Thank you. Hi, everyone. Welcome to this week's first lecture. Today, our speaker is Dr. Sean Clark. He will be giving us a lecture on Monte Carlo simulations. Dr. Clark has more than 10 years experience performing radiation detection measurements and Monte Carlo modeling. He has organized and performed numerous experimental campaigns involving measurements of special nuclear material with organic scintillation detectors and state-of-the-art digital electronics. His current interests are active interrogation systems for nuclear nonproliferation, safeguards, and treaty verification applications. With that, I'd like to present Dr. Sean Clark.
Thank you, Courtney, for the introduction, and it's my pleasure to be here today to kick off Monte Carlo Week. So my goal today is going to be to provide an introduction to the Monte Carlo method. So I'm going to talk about what the method is, give a little bit of history, and provide you with a number of examples that we can put this method in context and talk about some of the ways we apply it in the field of nuclear engineering. My goal today will be to talk for around 40 minutes or so to allow time for questions. So if you do have questions, please, as usual, type them in using the Q&A tool in the webinar, and I will address as many of them as possible at the end of the lecture. So with that, I will go ahead and begin and talk about a little bit of the history behind the Monte Carlo method. So what is the Monte Carlo method? Well, it takes its history in the Manhattan Project, which was the code name for the project in the United States to develop the first nuclear weapon back in the mid-1940s. During that project, which was led at Los Alamos National Lab, which I'm sure many of you have seen the movie Oppenheimer, which goes into some of the details there. During that program, there were discussions about how they were going to perform the calculations to support this significant physics undertaking. And they had this supercomputer at the time that was called ENIAC. There's a photo of it at the right, and there's a link there you can go to if you want to learn more about it. But essentially, this was a supercomputer that had much less computing power than your cell phone, but weighed 27 tons and took up 1,800 square feet. But nevertheless, it was the supercomputer of the time, and it was theorized that this computer could be used to perform statistical trials to predict the behavior that they might observe for this physics they were interested in. So you can see at the pictures at the bottom are the three gentlemen who are credited with development of the Monte Carlo method in its infancy. Stan Ulam, Nick Metropolis, and John von Neumann. They were all scientists at the time and contributed various aspects to the development of this method. So that's kind of where it came from, but what really is it? It's interesting if you do a Google search or look in textbooks and various references. It's a little bit difficult to find a consistent definition for what really is Monte Carlo. So I've listed a few here on the slide. I'm not going to read through them all, but as you all kind of take a look and survey them visually, you can see a few themes that are popping out here. The themes of random numbers and statistical trials and things of that sort. So we can see that whatever this Monte Carlo method is, it's something that relies on statistical trials to develop the solution or develop understanding of some kind of physical process that you're interested in. So what I'm going to do in this lecture is show you some examples of how that gets applied, and work through those examples in increasing complexity. But suffice to say, the Monte Carlo method itself is some method that relies on random numbers and the use of those random numbers to solve some type of problem. So this first definition here at the top of the slide is probably the most general and sufficient description of the method itself. So how do we actually apply it? Well, again, we need random numbers. So in essence, the Monte Carlo method is just sampling a bunch of random numbers and using those random numbers um, to predict the behavior of some physical process, right? So these random numbers can be used to statistically sample some physical quantity of interest. And that physical quantity of interest can be anything as simple as the rolling of a dice or something as complex as the behavior of the neutron population in a nuclear reactor and anything in between. As long as the scientist has some understanding of the physical laws that govern those quantities, we can use Monte Carlo or random sampling to predict the behavior of those quantities. The third point there is an important one. So the Monte Carlo method, the quality of that estimate relies on the number of samples that one performs. So you can see only the reliability of the estimate is increased as the number of samples becomes large. So it's not sufficient to just do some random sampling. One needs to do a large number of random samples so that the reliability of the estimate can be high. So at the core of Monte Carlo calculations are random numbers. So in modern days, we don't use true random numbers. We use what are called pseudo-random numbers. And this is important because pseudo-random numbers, as the name implies, are not truly random. The reason we use pseudo-random numbers is so that these Monte Carlo algorithms can be implemented on computers. So the way that these pseudo-random numbers are generated, they're generated using a mathematical sequence. These are mathematical recursive relationships whereby one random number depends on the previous random number in that sequence. So it's a mathematical function that's used to produce a series of numbers that satisfy some test for randomness. So they're not truly random in the strict sense, but they are quote unquote random enough that they can be used in Monte Carlo. So there are some properties of these pseudo-random numbers that have to be followed. You can see them listed here on the slide. Firstly, these numbers are uniformly distributed on the interval between 0 and 1, so they're normalized. So it's a series of numbers that are normalized on 0 to 1. The second property is that they need to be produced quickly, speedily. And the reason for that is because Monte Carlo calculations require a large amount of random numbers. Orders of magnitude, millions, billions of random numbers are needed to perform even a simple physics-based Monte Carlo calculation. So the need to produce them speedily has to do with how efficient these computer codes can be and how quickly we can solve problems. The third property is they need to be reproducible, meaning if one creates a random number string and then you come back and do it again, you should get the same series of random numbers, pseudo-random numbers. And this has to do mostly with debugging. So if you're trying to write a computer code that's solving a Monte Carlo problem, if the numbers were truly random, the solution would be different every time the user ran the code, which is not ideal when you're trying to write some code that you want to, make sure is working properly. So these numbers, because they're coming from some mathematical algorithm, they are by definition reproducible as long as you start with the same initial random number, which is often referred to as the seed. And the fourth property is a long cycle length, which means cycle length is how many pseudo-random numbers can be produced before the series begins to repeat itself. So because these are developed using mathematical relationships, the series will eventually reproduce itself. So if random numbers are being reproduced in the same series, then that violates one of the goals of Monte Carlo, which is having a large number of independent trials. So the numbers need to be random for a long time before they begin to repeat themselves. Modern random number generators have cycle lengths on the order of 10 to the 14 or even higher. So we have generators that exist that can produce very long series of random numbers. There's algorithms listed at the bottom, a set of bullets there that you can investigate if you're curious. But any sort of scripting language that you find, like MATLAB, Python, even Excel, has an ability to create random numbers. So this is the first and most important thing about Monte Carlo is you need access to some series of random numbers. The second most important bit of Monte Carlo we need to understand is the central limit theorem. So the central limit theorem is the mathematical theorem that sort of underpins all of Monte Carlo. And essentially what it says is that regardless of the distribution of the parent population, if you sample it enough times, it's going to converge to a normal distribution. Regardless of the parent population is key. So if we have any distribution that we understand that has a finite mean and a finite variance, if we take enough samples from that distribution, we will end up with a normal distribution, which allows us to perform random sampling and use that random sampling to estimate the quantity of interest. So whatever quantity that the parent population defines, we can sample it and then predict from those samples. We can set confidence bounds, we can put error bars on our estimates. All of this comes from the central limit theorem. There's an example here in the middle of the slide talking about Bernoulli trials. If you imagine a situation where you have a series of results that are simply zeros and ones, clearly 0 or 1 is not normal distribution, but if we take that long series of results and group them into subgroups, the distribution of those means will in fact be normal. And that's a kind of an example of how even a distribution that's very obviously not normal, a Bernoulli sample of either 0 or 1, can still be looked at as normal if we group the results in a certain way. So this central limit theorem is the main piece behind underneath any Monte Carlo calculation. All right, so next on the list is vocabulary. So we need to talk about a couple definitions here. So I talked about Monte Carlo as a technique to sample from parent distributions or physical distributions. We talk about these in terms of probability density functions. I'll use PDF for short. And a PDF is what's used in Monte Carlo to represent the physical quantity that we want to sample. I'll give some illustrations of this later, but let's just consider P of X to be the distribution of some quantity X that we're interested in sampling. This is the important distribution that's required to perform Monte Carlo sampling. So in order for P of X to be a PDF, it has to satisfy two properties, and they're kind of illustrated by this equation in the middle of the slide here. The first property is that the PDF must be normalized, which is what this says. Integrated over all possible outcomes, it must equal 1, which means it's probability, so something must happen. When you integrate over all possibilities, something must happen. The other property is that the PDF has to be positive definite. We can't have negative probabilities. So if one has access to a PDF for whatever physical quantity they want to sample, you can then take that PDF and create the next important piece, which is the CDF, which stands for cumulative density function. In Monte Carlo textbooks, you'll often see PDFs as lowercase p of x, and CDFs will be written as capital P of x. They're related functions. As the name implies, the CDF is simply a cumulative integral of the PDF. The important thing to note here is while the PDF must integrate to 1, the CDF, capital P of x, remains a function of x. And this property of the CDF is what allows us to then sample from that distribution through the process known as random sampling. So if we have our CDF, capital P of x, which is defined in this way from the previous slide, in the next step, if one wants to do random sampling, is we simply take this capital P of x, the CDF, and we set it equal to some random number. And again, in Monte Carlo textbooks, it's often used, this random Greek letter xi is used to denote random number. So what we can do is if we have our CDF, P of x, which is a well-described function of x, we can set that equal to our random number xi, and then we can actually solve for x. Okay, so if p of x is a function of x, we set it equal to c, which is considered to be a constant. It's a random number, it's a constant. We can then solve for x as a function of c. And this is one example. It's called the inverse transform method. One example of how we can perform random sampling if we have a p of x that is well behaved. If it's analytically integrable, we can quite literally solve for x as a function of c. So then for a series of c values, random numbers that we get from our generator, those will directly correspond to a series of x values that are governed by this CDF p of x. This process of taking a CDF, setting it equal to random number, back solving, this is called random sampling. In particular, this is called the inverse transform approach. There's other approaches, rejection sampling, table lookup methods, all kinds of things that can be employed if this p of x is not easily integrable. But it's easiest to think about in terms of a p of x that is integrable. And then if that's the case, then you can simply solve that p of x for c, and then you have your series of physical quantities x. So that is the Monte Carlo method in a nutshell, but it's a bit esoteric so far. So I want to go through a few examples. Again, these will be of increasing complexity to show what it really means to, through random sampling, produce the physical quantities x in which we are interested in. So here's the examples I want to do in the next half an hour or so. So again, increasing in complexity, the first example is just throwing up a single die. The next will be a classical Monte Carlo problem called the hit or miss experiment. And then we'll get into things that are a little more nuclear engineering-y. The third will be a kind of a deep shielding problem, and then I'll end with what it would look like to simulate neutron random walk problem using Monte Carlo random sampling. So firstly, throwing of a die. So I'm sure everyone in the audience here has at one time or another in your life rolled a dice. Whether it's a single six-sided dice or a bunch of dice, you played board games, some type of situation. I imagine we've all rolled dice. So what we want to think about in this example is rather than rolling a single die, we want to think about how we would simulate those outcomes using the Monte Carlo method. So for this example, for the sake of simplicity, we're going to assume that the dice we're rolling have 6 sides. Of course, you can do the same example with a dice with 10 sides or 20 sides or whatever the case. But we're going to do this using just a single 6-sided die and think about how we can simulate that using Monte Carlo. So written on the slide here is just a way to kind of write out the problem mathematically. So if you imagine you have this physical dice in front of you and you're rolling it n times, you can think of your set of outcomes as some big N number of little n's, where n sub I is the outcome of the ith throw. So these n's are going to be either 1, 2, 3, 4, 5, or 6, because again, we're assuming that the die we're rolling here has 6 sides. So if you had these outcomes in front of you, you could, just using arithmetic, compute the average outcome from rolling a single 6-sided die. Just by adding up all of the outcomes, all the different outcomes that you observed physically, and dividing it by the number of throws n, that would produce the result. The well-known average of a 6-sided die outcome is 3.5. So if you did this enough physically, you would compute this and you would get 3.5. But that would take a while to roll all these dice, because clearly you would need a large number of rolls to produce accurately this average n. But we want to do this using Monte Carlo. So we want to simulate a large number, n, throws of a fair 6-sided die by generating random numbers. And if we can do this by generating random numbers, we can do it very quickly and efficiently on our laptops, either using Python, MATLAB, even Excel could do this. Again, we're going to assume a six-sided die here, which means we have six possible outcomes, 1 through 6. And we're also going to assume that our die is fair. And what I mean by fair is that the outcome of all six sides is equal. The chances of getting any of the outcomes is the same. So the first thing we have to do when we want to do random sampling is to construct or understand our probability density function. So in this example, it's actually a special case. It's a discrete PDF because we have six discrete outcomes. So our discrete PDF in this case is just a set piece of I where each piece of I 1 through 6 is equal to 1/6, because again, we're assuming that our die is fair. So our PDF is just the step function, everything is equal to 1/6. Once the PDF has been constructed, we can consider the CDF as the cumulative integral of that CDF. In this case, because our function is discrete, instead of a cumulative integral, it's a cumulative sum. So the probability of X, an outcome less than or equal to I, where I is 1 through 6, is equal to the sum of P from 1 to X. So for example, the probability of getting 1 is just 1/6. The probability of getting 1 or 2 is 1/6 plus 1/6 is 2/6. That's the CDF. And actually, it's probably easier to explain visually here. So this is a visual representation of our CDF. So you can see written here, lowercase p, these are the PDF values, and the uppercase p, you can see it's building to our CDF. So the probability of getting 0 is just 0. Probability of getting 1 is 1/6. Probability of getting 1 or a 2 is 2/6, 1/3. The probability of observing 1, 2, or 3 is 0.5, so on and so forth. All the way up to the top, the probability of observing a 6 or less on a single six-sided die is 100%, because if you roll it, you have to see something. So this is a visual representation of a discrete CDF. So you can probably already see how this works visually. So our CDF is just this cumulative step function that adds up to 1. So what we would do in our Monte Carlo calculation on our spreadsheet or MATLAB is we would sample a random number, which is going to have a value between 0 and 1. This is the way pseudo-random numbers are defined. We would sample a random number and figure out into which of these bands it falls. Okay, so if the random number gets sampled, then say it's like 0.6, it would land in this band, which will correspond to an outcome of 4. You could sample another random number, say it gives us 0.4, it will land in this band, which corresponds to an outcome of 3. So essentially, you're producing a series of random numbers, figuring out which band they fall into in the CDF, and then assigning those bands the outcome of the corresponding die value. And doing this, you could produce as many dice outcomes as you so desired. And then from those outcomes, you could compute the average, which given enough trials would result in the true value of 3.5. Okay, next example. This is going to be a continuous example. So the first one was discrete outcomes of six-sided dice. The second example I want to talk through is hit or miss experiment. So this is a situation, it's another kind of thought experiment problem where for whatever reason, you want to compute the area of this green surface S. And this green surface S is a surface which is not easily defined by any mathematical equation. It's not a nice surface that you can compute the area of like analytically. But what we can do is consider another surface. In this case, it's this box, this purple box that surrounds S. We can consider another surface that bounds S that is easy to compute the area of. So in this case, we have this area. The area of the square is just b minus a times d minus c, just the product of the two side lengths. So we can compute the area of the square quite easily. So how do we get the area of the surface S, only knowing the area of the bounding square? So we can do this by considering a situation where if we had this surface physically laid out in front of us, we could throw darts at this surface. And if we did that, some number of darts would land in S and some number of darts would land in the surrounding box. And if we did that for a large number of times, we could say that lowercase n darts hit the surface S. And if we divide that lowercase n by the total number of darts we threw and multiply it times the area of the rectangle, that ratio would give us the area of the surface S. In this case, I call it A. So the question is how to do this again with Monte Carlo. We don't want to sit here and make these surfaces and throw darts at a dartboard. We want to compute this with Monte Carlo. So we can do this by sampling positions which correspond to the coordinates of the virtual darts that we're throwing at this page. So in this case, we want to sample our positions, our dart throwing positions, uniformly across the rectangular region, the purple region on the previous slide. And to do this, we need to generate pairs of random numbers that are going to correspond to X and Y coordinates in that rectangular space. So in short, we want to simulate using Monte Carlo a value of X that's between A and B, the X direction, and a value of Y that's between C and D. And if we can sample those two numbers, that will give us unique positions on this surface. You can probably see that it's just a linear interpolation between A and B, for example, for the X coordinate, but this slide shows you how you can work that out using the random sampling approach that we've talked about earlier in the lecture. So for the example of the X coordinate, our PDF in this case is uniform. So our P of X dx is just some constant times dx because it's flat. We want our X coordinate to be sampled uniformly. But this P of X equals C times dx is not normalized. So it has to be normalized over the interval between A and B. So if we integrate our PDF, which is just C dx, over the integral A to B, set it equal to 1, because again, we're normalizing, solve for C, that gives us a constant C equal to 1 over B minus A. We plug that back into C and then solve this integral for the inverse transform method and then solve for X, we end up with this linear interpolation equation that we have at the bottom of the slide. Same exact approach applies for the Y coordinate. It's just instead of between A and B, it's between C and D. And if we sample using these random numbers, so if we grab pairs of random numbers, C and eta, important to note that these random numbers are different because we want the X and Y coordinate to be sampled independently from one another. So we need one random number to give us X coordinate, another random number to give us the Y coordinate. And if we do that, we will thereby generate pairs of coordinates, X and Y, that can be correlated to coordinates in that rectangular region. And if we take that ratio, that'll allow us to estimate the area of the surface S. Comments, I already kind of mentioned this, but just to put it here for completeness sake, the X and Y are independent variables, which corresponds to the dart being thrown truly randomly. You're not aiming, for example, right? And the other property is that these endpoints must be chosen uniformly over the entire rectangle. We have to fully sample that surface, that rectangular surface, in order for this ratio to truly work out to the area of S. Okay, thirdly, we're going to get to some nuclear engineering here. So last two examples, this one is deep penetration problems. So we're going to consider particles that are incident on a shielding slab. And we want to think about how we can compute the probability that particles will make it through that slab. This is kind of a fun example that you can do in a group because you can actually do this calculation using physical dice. So instead of using random number generator, you can actually use dice that can be rolled to predict the outcomes of these various particle histories. So what do we mean by shielding problem? So this is the idea We consider a shielding calculation where the shielding slab, which is the boxes here, each of these is it's 4 slabs thick, and we consider each of these slabs to be 1/2 layer. So whatever the shielding material is, we consider each of these thicknesses to be a half layer, meaning the probability that a single particle makes it through that layer is equal to 1/2. So if the shielding is 4 half layers thick, the probability that any given particle makes it through is 1/2 times 1/2 times 1/2 times 1/2, because there's 4 layers, which is equal to 1/16. So we can very easily compute this analytically, that for a shielding block that is 4 half layers thick, any given particle has a 1/16 or a little bit more than 6% chance of making it through. So the question is, how can we do this with Monte Carlo? Well, because our shielding probability is so straightforward, it's a binary, it's 50%, makes through or it doesn't, we can go back to our dice and we can use dice to actually solve this problem. So if you had a large number of dice you wanted to roll, you can even use your dice algorithm from example 1. You could figure out whether or not any given particle is transmitted through a slab or absorbed in the slab based on the outcomes of those dice. So we could do this in a large room. We could have everybody stand and everybody rolls the dice. Anybody that rolls a 1 through 3 gets absorbed, so they would sit. Anybody that rolls a 4, 5, or 6 transmits, so they would remain standing. We could do this 4 times, and we could calculate the transmission probability as the number of particles that made it through all 4 slabs divided by the number of people or particles that we started with. And clearly, if we have a low number of scores, we can't assume we're going to get exactly the analytic solution of 0.06. If we only start with 20 particles or even 10 particles, it's very, very likely that we will not get the true analytic solution of 1/16. But what we can say is, this is the illustration of how we compute error. The error in our estimate is going to be related to 1 over the square root of the number of scores. So if we truly did this calculation and we started with 16 particles and 1 particle made it through, we would get a value of 1/16. We had 1 transmitted particle divided by 16 particles we started with. But the uncertainty in this 1 would be 1 over the square root of 1, which is 100%. Because we're just as likely to get 0 as we are to get 1, because we only started with 16 particles. So this kind of illustrates how, to truly get a good estimate using Monte Carlo, you need a large number of trials. In this example, a large number of trials, initial particles, will result in a large number of scores, which then will result in a small uncertainty, because the uncertainty is related to 1 over the square root of the number of scores. Last bullet I'm not going to spend any time on, because just for the sake of this lecture, but there are ways in Monte Carlo to improve these statistics without just simply running more particles. There's approaches called variance reduction. One of them is particle splitting, where you can actually artificially increase your particle populations to allow for reduced uncertainty. So if you're interested in that, you can look up variance reduction or particle splitting, and you can find lots of resources online. But for the sake of this lecture, I'm just gonna leave it at that, where the uncertainty here is gonna be 1 over the number of scores. All right, so the last example here in the last 10-ish minutes is neutron random walk. So in this case, we want to think about now more physically how we can simulate the properties of a neutron that's bouncing through some region of space using the Monte Carlo method. So we're not going to go through huge detail here, but I want to talk about some of the physical properties of this neutron we can simulate using Monte Carlo. We can simulate the direction, the energy, how far it travels. All these things are governed by physical equations that are easy to understand, easy to integrate, and easy to sample using the Monte Carlo method. So I'm just going to skip some of the pictures in the interest of time, and talk about what we mean by random walk. So when we say random walk, in terms of neutron transport. We call it that because the neutron transport is fundamentally stochastic. Um, Everything about the neutron's life in this region is random. Um, the energy a neutron is born with is often random. The direction it's born traveling is generally random. How far it travels from one collision to the next is random. Once the neutron collides, what type of collision happened? Also random. I think you get the point here, right? So in order to fully simulate a neutron random walk, we need to have physical PDFs that govern all these properties that we can then put together and ultimately um, build the random walk of this neutron. So if we think about our our toy problem here, where we have a neutron incident on this slab, the first thing we would need to do if you wanted to do this Monte Carlo calculation yourself is you would need to generate a source particle. The source neutron has to be born, and then it can be transported, right? So in our simple problem here, we're just assuming this neutron is born at the edge of the slab, but we have to provide it with some energy and some direction. Generally, in Monte Carlo calculations, these these properties are sampled independently to one another. So the energy of the neutron is not necessarily related to the direction. It can be, but not always the case. In this case, we're going to assume they're independent. So let's just say we have a neutron source and we know the energy. So we can assign some energy to the source. We could also sample it from a Watt spectrum or some other spectrum, some other function, but let's assume we know the energy. So we have our neutron source and we've sampled the energy. So the next question we have to ask is, which direction does the neutron travel? And this is more interesting. So um, we're going to assume that our neutron source, whatever the source is we're trying to simulate, emits neutrons isotropically, meaning any direction of emission is equally probable. And we can describe that probability using PDF, right? P of omega d omega over 4 pi, because 4 pi is the integral of all possible solid angles. So the neutron has to go somewhere. And if you look over all 4 pi, you will find that neutron. So this is what this PDF says, that the neutron is emitted in 4 pi, and each angle, each direction is equally probable. The math here, I'm not going to go through it. I think you'll have these slides after the fact, so you can do this at your leisure. But basically, we can assume this d omega is separable into two angular components, theta and phi. And by integrating those PDFs into CDFs and sampling, we can produce expressions down here as a function of xi and eta, similar to how we created pairs of coordinates in x, y. We're creating a direction with two components, theta and phi, that can then be used to construct the direction vector of that neutron. Okay, so this slide, here's a recipe for how you can simulate using Monte Carlo a single direction that is isotropic over 4 pi using sets of random numbers. Okay, so if the neutron source has energy defined on the previous slide, we grab two random numbers and we sample the direction using this inverse transform method. The next thing we would have to ask is, how far in our region of space does the neutron travel? Again, this is random. Neutron transport, neutron attenuation is governed by this e to the minus sigma r, where sigma is the cross section. And we can, again, normalize that, construct the CDF, do the inverse transform method, and at the end of the day, we arrive at this expression that relates some distance r, meaning how far the neutron travels, as a function of the total cross-section, which is related to the interaction probability, as a function of the total cross-section, and some random number, c, we can sample how far this neutron travels in the slab. Okay, so now we've used three random numbers, two random numbers to get the direction, one random number to get how far the neutron travels in the slab. And the last thing we have to ask ourselves is, which type of collision happens? Okay, so we know the neutron travels some distance r in the slab. The next question is, once the neutron travels that distance r, which kind of collision occurs? Collision types in nuclear data are governed by this quantity called a cross-section. In this case, it's a macroscopic cross-section, and there's a separate cross-section for every possible interaction. So I listed a bunch of them on this slide: N, N prime, gamma, fission, alpha, 2N, 3N, etc. There can be any number of these individual cross-sections called partial cross-sections for the various types of collisions that neutrons can have in that medium. So if we have all these partial cross sections, we can normalize them. Okay, so this approach kind of goes back to the first example we talked about today, which is the discrete PDF of the dice. This is very similar, only this dice has many more than 6 sides, and it's no longer fair. Each of these probabilities is not equal, right? These reactions are not necessarily equiprobable. So this is equivalent to rolling an n-sided unfair die, but otherwise it's the same theory as that dice example we showed a little bit ago. So we can say that the partial probability, the probability of some reaction X, is equal to the partial cross-section for that reaction divided by the total. So in the dice example, it was 1/6 everywhere. In this case, it's sigma sub X over sigma total. And from that data, we can construct a step function just like the dice. And using that same approach, we can, through random sampling, figure out which type of interaction, sigma sub X, the neutron had at a given position. So with that approach, we have a source neutron that traveled some randomly sampled direction, some randomly sampled distance, and had some randomly sampled interaction type. That is the full life of that neutron from birth until whatever collision it has. Now, once the collision happens, we would need to figure out, okay, what happens from there? Is it a scattering interaction that scatters the neutron in an isotropic direction? In which case, we could just sample a new direction, then a new distance, so on and so forth. If it's a fission, we'd have to make more neutrons, and it gets increasingly complicated. But this illustrates how we can use random sampling to sample each of these physical quantities, right? Isotropic direction, distance governed by a cross-section, reaction types governed by partial cross-sections. These are all physical parameters that we can take and create a series of Monte Carlo sampled realities. This is about scoring. I'm running low on time here, but I think this is kind of the end. So I skipped over the particle weighting piece of the tally, but there's essentially 2 ways we can do Monte Carlo. But essentially what we're doing is we're counting outcomes. Okay, so in this case, if we're producing these neutron random walks, and we're interested in how many neutrons make it through a certain slab, we can just count the number of neutron events that end in capture or that escape the slab, so on and so forth. If we want to use some kind of weighting, then those weights are not 1, but that's a little bit beyond the scope of this lecture. So in summary, just a couple closing thoughts here. The Monte Carlo method is an approach that relies on a large number of independent statistical trials to solve a problem. That's the summary. There's a number of advantages to the method. It's an efficient technique that can be used for multidimensional problems, which is problems that can't be solved analytically. We can use Monte Carlo to solve the problem numerically. It uses nuclear data directly, which is kind of an important note. If other approaches that use energy grouping and things, those are all approximations that get introduced into the nuclear data. So the Monte Carlo is using the data directly, which is often a more accurate way to do things. And because of this, because it's based on direct nuclear data, there's no homogenization, all this stuff, it's often considered to be a numerical experiment that gets used to validate these deterministic codes, which each introduce their own assumptions and approximations. However, there's no free lunch, so to speak. There are some disadvantages to Monte Carlo because it's using the base nuclear data without homogenization and grouping. It can result in large memory requirements because all of the data have to be loaded into memory that then get used to perform all these Monte Carlo samplings. So you can end up in a situation where you need lots of memory. Although these days memory has gotten relatively inexpensive, so that burden has been reduced, but it's still nevertheless a reality. Second disadvantage, which is probably more significant, is that because the error on our estimate is related to the number of histories or particles we simulate, sometimes, depending on the problem, you can encounter a situation where you have long run times. Again, modern computers have gotten pretty fast, so for relatively like lab scale type situations that you want to simulate, it's not generally prohibitive. However, if you think about simulating, a full power nuclear reactor core, those problems are still somewhat intractable because of the runtimes and, frankly, the memory requirement. So, with that, I've just got a few references here that you can find online and read at your leisure. And I'll stop and take the last 10 or 12 minutes here for questions.
Thank you, Dr. Clark. Now we'd like to open the floor for questions.
I'm getting an echo from you, Courtney. I think maybe you're in the bare room, but I see a few questions in the chat, so I'll just start with them. So first question, does Monte Carlo require a supercomputer to be ran? No. So I should say there's a few commercial Monte Carlo codes that can be accessed, and later this week. So tomorrow we're going to hear a little bit about GM4, which is an open source Monte Carlo toolkit. And I think the Thursday lecture is going to talk a little bit about MCMP, which is another Monte Carlo code that's developed by Los Alamos National Lab. There's also some other open source Monte Carlo codes that you can find online. Any of these codes can be ran on, say, a laptop. I run MCMP on my laptop routinely, so you do not need a supercomputer to run Monte Carlo in general. That being said, if you're trying to do, again, like a full-scale nuclear reactor, things like that, those demands could increase quickly, so you may need more computing power than a typical laptop could offer. Next question, how to determine how many histories to run in a Monte Carlo simulation? This is a very good question. The short answer is there is no a priori way to know how many histories one needs to run, because it depends on the efficiency of your Monte Carlo model, right? So for any given source history that is simulated, it needs to score whatever quantity you're trying to calculate. And that efficiency determines how many histories need to be ran to achieve good statistics on that scored quantity. So it's not a priori. You can't really figure that out. However, what you can do is often figure out in a relative sense, how many more histories do I need to run? So we know that a relative error goes like 1 over the square root of n. So if we run a simulation and we see an error of 10%, say, and we run an error of 1%, we know we need to run it like 100 times longer because it's 1 over the square root of n. So to get a 10 times reduction in error requires 100 times more histories. So in a relative sense, you can compute it. A priori, you cannot. Let's see. Actually, that goes to this question as well. How can we rigorously estimate the convergence rate and the error bounds of Monte Carlo for high dimension integrals? Yeah, so in this case, to get to the first sub question here, the uncertainty in these estimates, again, it's very proportional to 1 over the square root of n. So you can use the central limit theorem, and there's expressions for how to compute the confidence intervals with those estimates, but basically it's related to the central limit theorem and how many scores that are achieved. Optimization problems. Moving too quickly. How can Monte Carlo methods be effectively integrated, combined with other optimization techniques, simulating annealing? Yeah, this is a good question about combining Monte Carlo with other techniques. So there are, in some of these commercial codes, like I mentioned, like Monte Carlo, GM4, there are approaches in these codes that combine both the stochastic Monte Carlo approaches with some analytic estimates. So I think this question is a little bit general, but I'll just say that it is doable, and there are commercial codes that do that very well. If it's for a more general problem, that would need to be developed by the user, but certainly it is doable. How attendance is done. Is the random number generator different for different problems that are similar in nature? Yeah, this is a good question. So the random number generator that is used in Monte Carlo um, is generally whichever one's available. So, for example, in MCMP, which is the code that I'm most familiar with, I think in this code there are 3 or 4 different random number generators that the user can choose from. Each of those generators is sufficiently random, meaning that they pass all the tests of randomness that I talked about earlier in the lecture. The difference in them is generally the cycle length. So the cycle length, again, is how many random numbers can get produced before the string begins to repeat itself. So that's generally the only concern that you have when you're using these generators from like packaged code systems. Any generators that are implemented in there are sufficiently random, but the question is how many numbers can they produce? So generally, the generators with a longer cycle length are a little bit slower to compute the number. So it's a trade-off between how efficiently can the random numbers be produced versus how many of them can be produced before it reproduces. So if you're looking to choose a random number generator, those are the two things that I would look at. What's the cycle length and how complex is the mathematical function? Alternatives to MCMP that are as effective. Yeah, I'm not really equipped to compare and contrast all the possible Monte Carlo tools that are available, but again, Giant4 is probably the most complex with the most flexibility. It's a toolkit, so it requires the user to have some experience with C++ and writing source code, but it's very customizable. Whereas MCMP is a more commercial product that's out of the box. Those are, I would say, like 2 extremes. And there are other codes that are in between in the continuum, something like OpenMC, for example, which is also open source. It's not as flexible as Giant4, but it's not as kind of out of the box rigorous as MCMP. So let's see, group energies at the end. Yeah, okay, good question. So this question is about energy groups versus how we score outcomes into bins. The energy grouping piece that I was mentioning on the previous slide had to do with the nuclear data. So the nuclear data that are used in Monte Carlo are not energy grouped upfront. So we're using point-wise cross-section data. The tally scores, the outcomes that are scored in Monte Carlo are again scored with the exact energy value, but the user, generally speaking, puts these results into bins. Essentially, it's creating a histogram. So it's not introducing any kind of approximation. It's just histogramming the tally results into bins that are specified by the user. How is the Monte Carlo method used to validate deterministic codes? Good question. So usually, the piece that's trying to be validated are approximations related to energy grouping of cross sections. Okay, so again, the nuclear data for deterministic codes is generally treated in energy groups. So instead of point-wise energy, we are looking at groups of energies for cross sections, which that's obviously an approximation. So Monte Carlo can help to quantify how significant is that approximation. The other approximation that Monte Carlo can be used to sort of quantify, and I think I had it listed up here. Yeah, so geometry homogenization. So in Monte Carlo, you're generally building the geometry using very detailed combinatorial volumes, whereas in a deterministic problem, oftentimes spatial regions are homogenized just to make the deterministic problem a little more tractable. So Monte Carlo, because you're modeling each cell in detail, it can be used to quantify again how significant that approximation was. Open source deterministic codes. I'm sure there are, but I'm not in a place to recommend any, but I'm sure that you can find some of those online. Um, Jumping around. I think one last question. Monocolor works on swinging most screen values. Yeah, so random number changes to get more hits than misses. Yeah, it's a good understanding. So there are ways to say optimize the Monte Carlo transport. So if you're doing a simulation, so if we think about the third example I showed today with the deep penetration shielding problem, we know how many what the probability is of a single history making it through that shielding. So there are ways in Monte Carlo to optimize the transport and actually change some of the physics and then kind of correct for that on the back end of the tally to really optimize how efficiently each individual history can score the tally. And this is a class of techniques called variance reduction. The codes I've been mentioning, GANT4 and MCMP for sure, has several built-in approaches for this. But if you're generally curious about that class of techniques, and some of them do indeed use machine learning, you can look up variance reduction. So with that, I thank you all again for your attention and your great questions, and I look forward to seeing you tomorrow as we continue Monte Carlo week. So thanks again for all your time.